Here are some properties of the correlation coefficient that you might find useful. So first off, they're between -1 and 1, where if it's 1, it implies a exact linear functional relationship between x and y. That is, y equals then you can write y equals ax plus b for some values of a and b where a is positive. And if it equals -1, then you can write y equals -ax plus b for some value, positive value of a there, which becomes negative with the sign, plus b. And that's the only way you can get correlations of 1 or -1. If it's 0, it means it's uncorrelated. So correlation is unitless. Kind of like a probability. It doesn't have units, even though x might measure something in meters and y might measure something in pounds. They don't have to be related at all. Correlation has no units. Unlike covariance, which would have like pound meters, which wouldn't make any sense. So when you do a linear function like this, you go something like ax plus b, and you want to, so z equals this, then the correlation between z and y, if you know the correlation between x and y, then these are generally the same, with some exceptions. If you multiply x by 0, if you take a equal to 0, then you're looking at the correlation of y with a constant, which is 0. It's uncorrelated. The other exception is if a is negative, then it flips the sign of the correlation. So if they're positively correlated before, they'll be negatively correlated afterwards. And similarly, if they're negatively correlated, multiplying by a negative constant, they'll become positively correlated. So rather, I should say absolute value. Another thing is to watch out for outliers with correlation, because you're drawing the best fit line. So sometimes if you have some big outlier, for example, on this graph, if we had an outlier way up here, then that would pull this line way up there, and that would really mess up our correlation coefficient. So be careful of those. And what statistics class would be complete without reminding you that correlation does not imply causation. So just because two variables are correlated, it does not mean that one will cause the other. One more thing I want you to know is about the sum of random variables. So when we take a linear combination of random variables, for example, z equals a times x plus b times y, we have in this class many times used the property that the variance of z equals a squared times the variance of x plus b squared times the variance of y. But that's not the whole story. There's another term here. This is true if and only if x and y are uncorrelated. otherwise there will be a covariance term here. So the covariance term is 2 times AB times covariance of x and y. So this is the actual formula that always holds, regardless of the correlation between covariance between x and y. So here's an example of that. So we can use this to calculate the mean and variance. If we have z is equal to, say, 2x plus 3y, we have variance x equals 1, variance y equals 2, and covariance of x and y, say that equals -1, because covariances, unlike variances, can be negative. So then we can apply this formula. We have the variance of z is equal to 2 squared times 1 plus 3 squared times 2, and then plus 2 times 1, times 2 times 3 times -1. Plug this into your calculator or do it in your head. You get 4 plus 18 minus 12. 22 minus 12 is equal to 10.